In this last thermodynamics lesson, we're going to look at Gibbs free energy, which is the energy that's available to do work in a system. Being able to calculate Gibbs free energy is going to help us to take into account both the enthalpy and entropy effects of a process to help us to determine if a particular process is going to be spontaneous. Now, we've discussed the fact that when a reaction is exothermic, it tends to be spontaneous. And when a system has an increase in entropy, that's also going to be favorable and lead to a spontaneous reaction. Now, these two factors can work together, like in a situation where a reaction is exothermic and the entropy is increasing, or they can work against each other, like in an example where the enthalpy is positive or the reaction is endothermic and the entropy is increasing. So what we need to do is take into account both of those factors in order to decide if a reaction is spontaneous, and calculating the Gibbs free energy is going to help us to do that. The Gibbs free energy equation that we're going to use, one of the main equations we're going to use, is delta G is equal to delta H minus T delta S. Now we're going to discuss why there's the temperature and why there's a negative sign here. So when a reaction is exothermic, the delta H is negative, and when you've got an entropy that is increasing, the delta S is positive. Gibbs free energy allows us to decide if a reaction is spontaneous. And when Gibbs free energy is less than 0, the reaction is going to be spontaneous in the forward direction. So this helps us to make sense with the fact that there's a negative sign in this formula, okay, because when entropy is increasing, that's a favorable process. So we want it to increase the Gibbs free energy in the negative direction. So by having a negative here, okay, we know when the reaction is exothermic and the entropy is increasing, it's always going to be a negative value for delta G, and so it's always going to be a spontaneous reaction in the forward process. The reason that we have to apply a temperature factor for our entropy is because you'll recall that entropy has the units of joules per Kelvin. And so we need to multiply by the temperature in order to give us the energy associated with that entropy. The reason we have that temperature included in the units is because entropy is temperature dependent. The higher the temperature, the greater the entropy. Now, one of the things that we need to do when we're dealing with the Gibbs free energy equation is be very mindful of the units, because entropy is often reported with joules, but as you know from experience, delta H is often reported in kilojoules, and it's just related to the size of the values. Okay? You could report either in the other unit, it doesn't really matter, but they have a tendency to be reported in kilojoules for delta H and joules for delta S because of the size of the values we deal with. Now, if the Gibbs free energy is negative, we know the reaction is spontaneous, and that means the opposite is true. If Gibbs free energy is positive, that means that the reaction is non-spontaneous. So an example of where we would have a non-spontaneous reaction always would be when we have an endothermic reaction where the entropy is decreasing. Okay, if we look at that formula, if the delta H is positive and the delta S is negative, this is always going to be a positive value for Gibbs free energy, which means that the reaction is non-spontaneous in the forward direction. It will be spontaneous in the reverse direction. Now, those are cases where delta H and delta S are working together in the same direction, but we can also have the opposite. Okay, so something like if we are evaporating Okay, if we're doing an evaporation, the delta H is going to be positive, and the delta S is also going to be positive because there's greater chaos in the gas than in the liquid. So what this can lead to is either a spontaneous or non-spontaneous process, and it really depends on the temperature. Because the delta H is going to be positive, depending on the size of the delta S and the temperature at which the process is taking place, this term can be larger than the enthalpy and can lead to an overall negative value for our Gibbs free energy, which would mean that we have a spontaneous process. We can also have an exothermic reaction where the entropy is decreasing, and in an exothermic reaction where the entropy is decreasing. Again, it depends on what temperature this process is taking place and the size of the relative entropy and enthalpies in order to decide whether the Gibbs free energy is going to be greater than or less than 0. So with the enthalpy having a negative value and the entropy having a negative value, okay, at low temperatures it's going to be spontaneous, but at higher temperatures this term is going to end up being larger than the delta H, which is going to lead to a positive delta G. Now when we have a decrease in free energy of the system is said to be exergonic, and when we have a system where the free energy is increasing, sometimes we call it endergonic. Okay, so this is, when we talk about exothermic and endothermic, we're really just talking about the change in the heat of the system. But when we're talking about exergonic and endergonic, it's related to the Gibbs free energy. These terms are used more often in biology. Now we talked about how when Gibbs free energy is less than 0, the reaction is spontaneous. When it's greater than 0, it's non-spontaneous. And when it's equal to 0, the reaction is at equilibrium. This fact we'll address later on in the lesson. Now what Gibbs free energy is the energy that's available to do work. So oftentimes in a system, the energy that's available to do work is lost in the form of heat. And what engineers are often trying to do is trying to determine ways that they can improve the efficiency of the system and ensure that that energy that's free or available to do work is not being lost to heat, but is being harnessed to do other things. Now, we're going to do a series of calculations for calculating Gibbs free energy using the formula delta G is equal to delta H minus T delta S. And there's going to be some certain factors that we're going to consider through the different examples. In our first example, we're going to be calculating delta G naught. And when you calculate delta G naught, we're going to use the delta H naught and the delta S naught from tables. One of the biggest things to consider when you're doing these calculations is to be mindful of the units, okay, which I've already mentioned, and I'll mention a few more times because it is one of the most common errors that people have when calculating Gibbs free energy. So we've got this process here of sodium chloride dissolving. We can calculate the delta H naught for this system using our heats of formation values from their thermodynamic tables. So we're going to take the free energy, the enthalpy of formation of sodium ions plus the enthalpy formation of chlorine ions, and we're going to subtract the enthalpy of formation of solid sodium chloride. Okay, so we're using that formula, the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Okay, and this is a very common way to calculate delta H. Okay, we learned 4 different ways to calculate delta H. Calorimetry and using heats of formation are the most common ways that you'll be expected to calculate the delta H. Okay, so for this process, the delta H naught is equal to 4.414 kilojoules per mole. Recall that the naught symbol means that this is carried out at standard conditions, which means that we are dealing with solutions that are 1 mole per liter and gases are at 1 atmosphere. It also is carried out at 298 Kelvin, which is 25 degrees Celsius. So this, as expected, dissolving a salt is an endothermic process. Okay, recall that for dissolving salts, sometimes they're exo and sometimes they're endothermic. Okay, it depends on the lattice energy of the salts and the amount of energy that's released when the ions interact with water. The delta S naught for this, also taken from the tables, is calculated in the same way. We take the entropies of the products and we subtract the entropies of the reactants. Okay, the units for this are joules per Kelvin, and for this process it's 44.37 joules per Kelvin. So as expected, dissolving the salt in water leads to an increase in entropy. Recall that ions have more options for how they organize in the solution, and therefore it's an increase in entropy. So now we're going to calculate delta G naught from that by taking our delta H and subtracting 298 times the change in entropy, and the change in entropy, you'll notice I changed it to 0.04437. I divided it by 1,000 because I was changing the units from joules to kilojoules. Okay, you have a choice of either changing your delta H or your entropy, but what you'll find is that Gibbs free energy tends to be in kilojoules, so that's why I chose to change my entropy over my enthalpy. Okay, and what I'm left with here is negative 9.08 kilojoules per mole. As expected, from our experience of dissolving salt in water, it's a spontaneous process. Okay, and the amount of energy available to do work from this dissolving process is 9.08 kilojoules. Now we can also calculate the standard free energy of formation of a compound, delta G naught F. And it's the same definition, or similar definition, to delta H naught F. You'll recall that delta H naught F is the energy released or absorbed when 1 mole of a substance is formed from its elements in their standard states. We're going to calculate the free energy of formation of ammonia, or NH3, using data in our tables. So what we're trying to do is find the Gibbs free energy of formation for ammonia, which is the delta G naught for this reaction. Okay, so much like in the last unit, we looked at deciding whether or not it was appropriate to label a particular reaction with a delta H naught F, we can do the same for delta G naught F. So in order to find the delta G naught F for this reaction, we're going to approach it using the same formula. Delta G is equal to delta H minus T delta S. So what we need to do is obtain the delta H naught F for ammonia, which we can get directly from the table. The value for that is negative 46.3 kilojoules. The delta S naught must be calculated because although the heat of formation is going to be 0, the change in entropy is not going to be 0 for this process. The difference between delta H naught and the S values is that these elements have an entropy associated with them. Unlike an element, the element N2 has no heat of formation. It's already in its most elemental form. Okay, so this is the main difference and the reason why we're doing this example, so you can appreciate the difference between entropies of formation and heats of formation. Okay, so the change in entropy for this system is negative 99.25. So now we've got our delta H and our delta S, so we can calculate our delta G. Okay, this time I'm putting it into the equation, my dividing by 1,000. Okay, you can do it before or put it in, doesn't matter. And I get 16.7 kilojoules per mole. Now in the thermodynamic tables, we also have delta G naught F's listed. And when we look up the delta G naught F for ammonia, we find that it is negative 16.7, which is what we expect based on this calculation. So because we have thermodynamic values for delta H naught F's for the Gibbs free energy, and because, like enthalpy and entropy, Gibbs free energy is a state function, meaning the process or the pathway that the reaction takes does not matter. All that matters is the initial and final states. We can calculate the delta G naught using the same type of formula where we take the sum of the delta G's of the products and subtract the sum of the delta G's of the reactants. So let's do an example for that. Okay, we want to find the delta G naught for the combustion of ethanol. Okay, so this is an example of where organic chemistry creeps into the AP exam, okay, where you're expected to write a combustion reaction for a particular organic molecule. Okay, we need to start with the balanced equation. Okay, and we need to calculate the delta G by taking the sum of the Gibbs free energy of the products and subtracting the sum of the Gibbs free energy of the reactants. As with the enthalpy and entropies, Gibbs free energy is an extensive process, meaning that it depends on the number of moles of the substance, and that's why we need to multiply by the coefficients when we're taking the sums. And like enthalpy, an element, like oxygen in this case, is going to have a value of 0 for the Gibbs free energy of formation. Okay, it's already formed because it is an element. And the value that we obtain for this process is 1300.5 with a negative sign. So the amount of energy that's associated is 1300.5. That's the amount of free energy. And the sign is negative, meaning that it's a spontaneous process. Now, example B here, we won't do. It asks you to find the Gibbs free energy for 1 mole of octane, okay, and we don't actually have the value in our tables. So we won't do that example. Now, one difference though between these two examples that I will highlight is that the way that the question is asked. So in this one, it's asking you directly for delta G. Here, it's asking you for the maximum work available, expressed in kilojoules. You need to be able to recognize that when it asks you for the maximum work, it is asking you to calculate the delta G for the process. Now, the examples that we've done so far have been examples where the temperature is 298. So the next thing that we're going to do is look at how the calculation changes when we're dealing at non-standard temperatures, so other than 298. For this, we're going to still use the same formula, so delta G is equal to delta H minus T delta S. And what we're going to do is use the temperature that is given for the process in the question. So in this particular example, we're going to calculate the delta G naught for this reaction at a temperature of 500 kelvins. Now, we are making an assumption here, and we're neglecting or ignoring the fact that the change of delta H and the change of delta S are independent of temperature. Okay? Delta H is pretty much independent of temperature. Delta S does undergo a change in entropy based on the temperature, but it's going to be small enough that we cannot worry about it. If we were an engineer and we wanted to actually determine the amount of free energy available and we were really concerned about the value that we get, then we would take other steps to find the change in entropy at the particular temperature. For our purposes, our main focus is to decide whether or not a reaction is going to be spontaneous or non-spontaneous at a particular temperature. So ignoring that fact about the temperature effect on entropy is acceptable. So the calculation really doesn't change much here. We need our delta H values and our entropy values from tables, so I'll just make a list here. So as expected for copper, the change in enthalpy is 0 because it's an element. Okay, and same for hydrogen. Okay, elements do have an entropy at a particular temperature. Okay, so these are the values from the tables. To calculate the delta H naught, we do the same process. The sum of the heats formation of the products minus the sum of the heats formation of the reactants, and we get 86.6 kilojoules. For the change in entropy, we take the entropies of the products and subtract the entropies of the reactants, and we get 151 joules per Kelvin. So to calculate the delta G naught at this non-standard temperature, the temperature is what changes in our final formula. So instead of using 298, which we've been using before, which is our standard temperature, we need to plug in the appropriate temperature that we're concerned about. Okay, so this process here is non-spontaneous at 500 kelvins. And this is an example where we've got an endothermic reaction. The entropy is increasing in the system, so it could potentially become spontaneous, but it's going to need to be even higher than 500 Kelvin in order to make it spontaneous or make this eventually become negative.